Welcome back to the BcT training course. This is a continuation of Module 4. This portion of Module 4 is Session 2, which focuses on the inputs to the BcT. We will use screenshots of the BcT software to overview the inputs, as well as use screenshots for the outputs and the results for rehabilitation design. As noted earlier for Module 4, a demonstration is included at the end of Session 4 that ties all of the screens together. There are 6 learning outcomes for Module 4 Session 2, which include: list the inputs to the BcT, import FWD deflection and layer thickness files, define the types of deflection basins, list the pavement temperature estimation procedures. The mid-depth temperature of the asphalt layer is important to interpret the outcome from back-calculated values for the asphalt layers. Designate the final segmentation. Explain the normalization of FWD loads and normalization of pavement temperature. This flowchart or diagram was included in Session 1, which introduced the guided process for back calculation using the BcT. Session 2 will overview the first 4 steps in the guided process. These 4 steps are: FWD data inputs, identifying the sensors to be used to segment the project into design sections, determining the segments to be used to back calculate elastic layer moduli, and finally, setting up or defining the pavement structure and layers to be used in the back calculation process. As identified in a previous slide, the topics for Session 2 correspond to the first 4 steps of the guided process that we previously explained. After accessing the BcT software, you will need to create a new project with the BcT and upload the FWD deflection files and layer thicknesses, if a layer thickness file has been created. After opening the program, the first screen is shown on this slide. So, to start with, click on the Create New Project. The software will automatically go to the next screen. The screenshot is provided in the next slide. A project file can be created using 2 paths. The first is to start from scratch, or the first time the project is created. This path first identifies the FWD file type and then uploads the FWD deflection data. A layer thickness file is then uploaded if available. The layer thickness file is not needed to execute or run the BcT. The second is when a project has already been created and processed. The BcT project created can be accessed to make revisions or updates to the files in process, which is identified by the BcT project name and the BcT project file path. We first need to identify the type of format for the FWD deflection basin data. A total of 6 FWD standard file types are recognized by the BcT. These deflection formats include a JILS.dat, a KUAB.FWD, a Dynatast v.20, a Dynatast F20 or SI, a Dynatast v.25, and an MDB. Chapter 2 of the BcT User or Help Manual explains the deflection and layer thickness file formats. For the BcT projects, 2 file formats are available. The first is for the legacy desktop BcT, and the second is for the web-based BcT project as displayed on the screenshot. This slide is just an example of an FWD file with the deflection and other input data. As noted on the previous slide, Chapter 2 of the BcT User or Help Manual explains and defines the deflection file formats. This slide shows an example of a layer thickness file. The layer thickness file format is a comma-separated values, or .cvs, from the ground-penetrating radar data or boring logs. An important point to remember: the stations in the layer thickness file need to match the stations in the deflection file for each design segment or project. For some projects, a layer may be absent where the layer thickness is 0 along the project. In other words, the layers are not continuous throughout the project from the GPR or boring data. The BcT layer thickness plots will stop when a 0-inch layer thickness is included for the first layer. So, if the material type for the first layer changes between different stations, that will define the limits of the segment or project for the back calculation process unless the layer thicknesses are manually entered. The user identifies the location or file path for the FWD deflection data and the layer thickness file path. As noted on the previous slide, the stations in the layer thickness file need to match the stations used in the deflection file. In other words, you cannot use stations for the layer thickness file and use mile marker locations for the FWD deflection data. After identifying the location of the FWD deflection data and layer thickness file paths, the user clicks on Create Project. After clicking on the Create Project button, the next screenshot is displayed in the next slide. The BcT will create a project file. The project file is displayed on this screenshot. The next topic covered within this session is on the FWD deflection data and other inputs. This slide displays a summary of the FWD data and other inputs needed for the BcT, which are displayed by numbers on the BcT screenshot. The screenshot shows the entire page, but the next few slides will focus on specific parts of the page. Most of the data gets populated in the BcT from the FWD deflection data file. The user should always check and make sure the data has been populated. The FWD data and other inputs include the error designations. Any errors in the file will be displayed in this location. All errors must be resolved before the BcT can continue. FWD plate radius. Sensor location. The sensor locations are defined by an X and Y axis coordinate system. Pavement temperature calculation. Test location, temperature, and GPS data. Deflection data. Target FWD load. Basin characterization. Each of the FWD data inputs will be explained further in the following slides. There are 7 steps in the BcT guided process as shown on this slide. Starting with Step 1, the FWD data. The BcT does a quick check to identify missing input variables from the FWD deflection file. When the user first starts a project, 2 common errors or missing data are the sensor locations and target load level. Some FWD files include the sensor locations while other files do not. If they are missing, the BcT will identify that missing information. When starting a project, the target load levels are not included in the FWD deflection file, so the user needs to manually enter those values. The target load level will be explained and defined in a later slide. The FWD plate load radius normally is included in the FWD deflection file. The location of the sensors is defined based on an X and Y axis basis. If the location of the sensors are excluded from the deflection file, the user will have to manually enter those values or upload the standard sensor location being used by the agency. As noted in the previous slide, sensor location data can be included in the FWD deflection data and will be automatically populated in the BcT. If the sensor locations are not included in the FWD deflection data, the locations will have to be manually entered or uploaded to the BcT. If manually entered by the user, those standard locations can be downloaded to a file so they can be uploaded on future back calculation projects using that FWD file format. A typical or standard location for many of the FWD test protocols is displayed on the slide and is defined on an X and Y axis basis from the loading plate. The next input variable is the pavement temperature calculation. Air and pavement surface temperatures are routinely measured during FWD deflection testing. However, mid-depth pavement temperatures are rarely measured during deflection testing for routine rehabilitation design. The mid-depth pavement temperature is needed to interpret the back-calculated asphalt elastic modulus values. The user can select the option to have the program calculate the pavement temperature or not. For most projects, the user will check the Yes button. The BcT includes 2 options to calculate the mid-depth pavement temperature. The 2 procedures included in the BcT are defined as the Southgate or Asphalt Institute procedure and use of the Bell's curve. Both procedures are discussed in Appendix F of the user manual. The Bell's procedure requires a previous day's average air temperature to deflection testing and the time the deflection testing started. The Southgate procedure requires an average air temperature for the previous 5 days prior to deflection testing. This is a screenshot of the station location, temperature, and GPS data listing from the FWD deflection data file. There are 10 types of data. The test point number is a consecutive listing of the FWD drops. This normally excludes the preliminary or seeding drops for each test point. The station or distance location marker for each test point identifies the longitudinal reference point for each test point. For area testing like parking lots or other similar facilities, This can designate the longitudinal distance and lateral offset. The lane designation can identify the direction, lane number, turning lanes, and other types of physical information. The test type designation is to identify the type of test like mid-slab readings, edge or corner readings, joint readings like for load transfer efficiency for PCC pavements and center lane or wheel path or cracked versus uncracked areas, and readings across transverse cracks for load transfer efficiency of flexible and semi-rigid pavements. Air temperature simply designates the air temperature recorded during FWD testing. Surface temperature designates the surface temperature of the pavement recorded during FWD testing. Pavement temperature records the temperature measured at the mid-depth of the asphalt or PCC layer. Pavement temperature readings are rarely made during routine deflection testing, so this field or column is usually blank for routine testing. Longitude and latitude information are the GPS locations of the test point. Elevation can be recorded by the FWD operator, but this column is usually blank for routine deflection testing. Date and time of the deflection test point. The user can review the information on the screen in comparison to the FWD operator's notes along the project. The FWD operator's notes are not included in the FWD deflection file summarized as part of the input data. Remember the target load that we referred to earlier in this session. This screenshot is for the user to specify the target load for each drop height within the FWD deflection data. The target load will be blank within the FWD deflection file, so the user will need to manually enter those values before proceeding. In fact, this is one of the parse errors that will be designated by the BcT as missing data that we discussed near the beginning of this session. Let's go through the definition and explanation of each column on this screen. The drop number is as defined for the previous slide and simply is a consecutive listing of the FWD drops and corresponds to the deflection data that was presented in the previous file. This tabular listing is available for each test point location and drop. The target load level is not used to identify the drop number in the sequencing used by the FWD operator along the project. The target load level is not used in back calculation. The actual load level measured during FWD testing by the load sensor is used. The target load level is only used to parse the deflection data into equal load or drop heights and is manually entered by the user. The FWD deflection files can have one or multiple target load levels. For routine rehabilitation design, one load level is typically used. The load lists the impact load measured by the load sensor. This is the value used in back calculation for each drop height. The next sets of 9 columns are measured deflections by each deflection sensor. The basin characterization is the final column and designates the type of basin for each test point. Basin characterization is defined on the next slide. The basin characterization classifies the deflection basin into 4 types of basins grouped as typical, type 1, type 2, and type 3. The x-axis for each graph is the distance from the loading plate, and the y-axis is the normalized deflection at each deflection sensor. The normalized deflection at each sensor is simply the deflection at the specific sensor divided by the deflection measured at the loading plate. The typical and type 2 basins are consistent with elastic layer theory, so the back-calculated elastic layer moduli can result in reasonable or appropriate values. These types of basins are when the deflections decrease with distance from the loading plate. The back-calculated elastic layer moduli from a typical basin will typically have better results between the measured and calculated basins from a type 2 basin. In other words, the calculated basins are closer to the measured basins for a typical basin than the type 2 basin. The difference between typical and type 2 basins is the rate of change in the decrease as illustrated in the graphs on the left. For the typical basin, there is a consistent change or rate of decrease the further from the load, but for the type 2 basins, the rate of change can have a different curvature within the basins, but the deflections measured by sensors further from the loading plate continue to decrease. Conversely, type 1 and type 3 basins are inconsistent with elastic layer theory. The back-calculated elastic layer moduli can result in inappropriate values. These basins are when the deflections do not decrease with distance from the loading plate. For a type 1 basin, the graph in the upper right, the deflections are greater than the deflection under the loading plate at one or more sensors from the loading plate. Obviously, this is inconsistent with elastic layer theory. The Type 3 basin, graph in the lower right, is defined when one of the sensors further from the load is equal to or greater than the deflection measured by the adjacent sensor closer to the load, but that deflection is still less than the deflection measured at the loading plate. This type of basin is also inconsistent with elastic layer theory. The next topic within this session is on the segmentation sensors. This is step 2 in the guided process, and the screen for the segmentation sensors is shown on the slide. The purpose of the segmentation process is to identify how deflections at different locations vary along the project and whether the project responses or deflection basins are statistically different. The items used for the segmentation sensors are listed on this slide, which is a screenshot of the segmentation sensors that are covered in the following 2 slides. These items include the sensors selected for segmentation, the target load level or drop number, the basin characterization designation, the test type designation, and the lane designation. As noted on the previous slide, this is step 2 of the guided process, segmentation sensor selection. The BcT allows up to 3 sensors to be used in the segmentation process. The BcT user or help manual provides some discussion on which sensors should be selected for the segmentation process. Any of the sensors can be used in the segmentation process. The intent is to capture as much information on the response of the pavement and subgrade as possible to understand how to break the project into design segments. Starting with the first sensor to be used for segmentation, it is suggested in the BcT user or help manual to use the deflection at the loading plate because this provides responses relative to the combined pavement layers and subgrade. The second sensor selected, or segmentation sensor 3, should be further from the loading plate. This will provide responses or deflections more controlled by the stiffness of the lower layers, like the subgrade. The third sensor selected, or segmentation sensor 2, is suggested to be a distance further from the loading plate that is greater than the bound layers. This will provide responses or deflection controlled by the upper bound and unbound layers. In selecting the second and third sensors for segmentation, it is suggested the user change the sensors to visually see how the magnitudes of the deflections for a sensor change along the project. The idea is to select those sensors for which there is an obvious change in the magnitude along the project. In summary, the sensor under the loading plate and the sensor further from the loading plate should be 2 of the 3 sensors used for segmentation in most cases. The third sensor selected should be a distance further from the loading plate than the combined thickness of the bound pavement layers like PCC, asphalt, and stabilized base layers that exhibit high stiffness. Now let's review other information included on the sensor selection segmentation screen. Continuing with the discussion of the other items included on the segmentation sensor selection screenshot. At the bottom of the screen, the thicknesses of the pavement structure will be displayed for the layer thicknesses included in the thickness file uploaded to the software. Remember, the layer thickness file can be uploaded from process GPR data or borings and cores. If a layer thickness file was not uploaded in step 1 of the guided process, this thickness graph will be excluded or will not be shown on this screen. The layer thicknesses, however, are not used for segmentation purposes. The layer thicknesses for each layer are used to determine if there is a visual correspondence between the deflections for the segmentation sensors and layer thickness. 4 other input variables or data designations are included on this screen that can be used in segmentation. The first is the target load level. All target load levels are displayed or included on the screen so the user can visually see how the different drop heights or target loads impact the deflection measured at a test point and along the project. However, only one target load level is used for segmentation, so the user must uncheck those target load levels that will not be used. The red note will continue to appear on the screen until just one target load level is selected. The second variable or item is the basin characterization designation. If the FWD deflection basin files include all 4 types of deflection basins, they will initially appear on the screen. The user needs to uncheck the basin types that will not be used to segment the project. Certainly, a Type 1 and a Type 3 basin should not be used. In fact, a Type 1 and Type 3 basin will not be used in the back calculation process. If the project includes a typical and Type 2 basin, both or only one can be used for the segmentation. It is suggested that the user keep each of the basin types checked while the others are unchecked to determine how many of the deflection basins are within each group or basin type. If a substantial number of the total are a Type 1 and/or Type 3, the entire FWD file may need to be reviewed to determine the reason because those data points will be removed from back calculation. We have previously defined test type and lane designations. All lane designations can be used for segmentation, but if there is a reason why a specific lane should be removed from the segmentation process, those lane designations should be manually unchecked. For the test type designation, the test points used for measuring load transfer efficiency, if any, should be excluded from the segmentation process because they should not be used for back calculation. Likewise, for PCC pavements, the only mid-slab deflections should be used for back calculation and thus segmentation. Any edge or joint readings or deflections should not be included for segmentation purposes because the discontinuity cannot be considered in elastic layer theory. The next topic within this session is on the final segmentation. This is step 3 in the guided process, and the screenshot for the final segmentation is shown on the slide. The purpose of the final segmentation is to identify areas along the project with different pavement responses. The items used for the final segmentation are listed on this slide, which is a screenshot of the final segmentation and is covered in the following 4 slides. These items include a preliminary segmentation, a statistical segmentation, and the layer material assignment for each segment. As noted on the previous slide, this is step 3 of the guided process, final segmentation of the project. For the segmentation process, there are 2 segmentation procedures used to identify areas along the project that respond differently to loads, which are 1, a preliminary segmentation, and 2, a statistical segmentation. The preliminary and statistical segmentation procedures are discussed in Appendix B of the BcT User or Help Manual. Remember, the first item when you import a layer thickness file in Step 1 of the guided process, the thicknesses of the layers are graphically illustrated along the project at the bottom of the screen. However, layer thickness is not automatically used for the preliminary or statistical segmentation. We will start with the preliminary segmentation. When the user clicks on a preliminary button, the locations where the responses change in terms of the area deflection method will appear for each segmentation sensor as vertical dashed gray lines that are shown on the screen. Next, when the user clicks on the statistical button, the locations where the responses are statistically different along the project will appear for each segmentation sensor as vertical dashed gray lines that are shown on the screen. The user can toggle between the preliminary and statistical segmentation to graphically compare the two, but will need to make a decision on defining the limits for each segmentation. The user can manually define the limits for different segments using the preliminary and/or statistical segmentation procedures. As an example, the user left-clicks on one of the dashed lines or on a separate location or station to define the beginning and end of the segment. The user-defined limits for each segment are designated as a solid red line in the screenshot. These can be manually defined using the deflections and layer thickness plots along the project. Again, remember, the layer thickness graphs or data is not used for the automatic segmentation. If the user wants to change the location, the user can simply right-click on the solid red line to remove the location. For this example, the user defined 3 segments which appear in a table on the screen as Segment 1, Segment 2, and Segment 3. The user defined limits of a segment that are vertical red lines and are consistent for all sensors and layer thickness plots or graphs, as shown on the slide. At the bottom of the screen is the layer structure table. The layer structure table only appears when a layer thickness file is imported into the program in Step 1 of the guided process. The user must manually assign a material type to each of the layers within the layer thickness file. The material assignments are discussed in the next slide. The last action as part of the final segmentation process is assigning a material type to each of the layers in the layer thickness file. For this example, 4 layers were identified within the GPR data, and are an asphalt layer or AC layer, a PCC fractured layer, a granular base, and a fine-grained soil subgrade. Remember, a maximum of 5 layers can be used in the structure simulation. The different material types are included in the drop-down screen. The user assigns a material type to each layer. The default layer properties for each layer type are in accordance with the MEPDG Manual of Practice. These assignments are included in Appendix C of the BcT User or Help Manual. The next topic within this session is on the structure definition. This is step 4 in the guided process, and the screenshot for the structure definition is shown on the slide. The purpose of the structure definition is to create the structure for each of the segments or to review the structure created from the layer thickness file imported in step 1. The items used for or related to the structure definition are listed on this slide, which is a screenshot of the structure definition and are covered in the following 4 slides. These items include the number of layers, layer type, layer thickness, Poisson's ratio, minimum and maximum modulus, and a seed modulus. As noted on the previous slide, this is step 4 of the guided process, structure definition. If the user imported a layer thickness file, the information for this screen will already be populated, so the user only needs to check the layer thicknesses and other properties for each segment. If the user did not import a layer thickness file, the variables on this slide need to be manually entered by the user. In terms of the variables and values of those variables, there is no difference in inputs between importing a layer structure file or having to manually enter the information. So let's now go through each of the parameters on this screen. When the program moves to step 4 on structure definition, the layer types, thicknesses, and other properties are not shown on the screen. Both the deflections and layer thickness plots are provided. Each segment is separated by a vertical solid black line. To retrieve the structure information, assuming a layer thickness file has been imported, the user left-clicks in the first segment on the deflection plot at the top of the screen. If a layer thickness file has not been imported, the user still left-clicks in the first segment, and the structure table will be shown. But the layer thickness and properties will not be included in the table and will be manually entered. First review: the number of layers and whether there is bedrock or a stiff layer as the subgrade are reviewed. The user can always make revisions to the structure by simply decreasing or increasing the number of layers and whether a stiff layer is present. If the user checks the stiff layer box, the last layer in the structure table will be the stiff layer. When a stiff layer is used, the user needs to manually enter the thickness of the subgrade and the material's properties for the stiff layer. When a stiff layer is used, the program will check the Fixed button. The user then enters the mean moduli for the type of stiff layer. For each layer included in the structure simulation or definition, the program automatically enters when a layer thickness file has been imported, or the user manually enters the values for each of the properties when the thickness file is not imported. The layer properties include layer type when the type of material defined in accordance with the MEPDG definitions, the average layer thickness for that layer within the segment, Poisson's ratio for that layer, a minimum and maximum layer modulus for that layer or material type. The BcT program populates the 2 fields with the expected or default minimum and maximum elastic layer moduli for that material from the default values included in the MEPDG. However, the typical minimum and maximum modulus values should be expanded because the default values represent laboratory measured values without any defects or deficiencies. That assumption is probably not true for most cases, so it is recommended that a very low minimum and very high maximum modulus value be used in the back calculation process to consider saturated or completely dry conditions, very aged asphalt or asphalt that exhibits severe stripping, and other such realities that can exist in the actual pavement layers. A mean or seed modulus of that layer, which is the typical average elastic modulus for that material, and whether the layer modulus is fixed. If the fixed bottom is checked, the program does not back calculate a modulus for a fixed layer, but it uses it in back calculating the moduli for the other layers. In addition, the fixed layer still counts as one of the maximum 5 layers. Relative to the fixed button, the user can always check that button, and the modulus of that layer will be fixed, and the mean or seed modulus value will be used in the back calculation process for the other layers. The fixed button is normally used or checked for any thin layer that is defined in the structure. After entering all properties for each layer, the user then clicks on the Apply button to accept the information entered on the screen for that segment. The user then repeats this process for each segment defined in Step 3, Final Segmentation. The Average Thickness button is for the user to reinstate the average layer thickness for the segment from the layer thickness file when the user changed the layer thickness for some reason or removed or added a layer. The information on the segments that have been completed and accepted is included in the upper right part of the screen with the percentage complete. After one of 3 segments has been entered, 33% will be shown. This screenshot is to simply show when a layer is added to the structure from the layer thickness file. In many cases for the layer defined by GPR testing, 1 subgrade layer is used. However, for back calculation, 2 subgrade layers can improve on the results by decreasing the difference between the calculated and measured deflection basins. The 2 subgrade layers are typically a weathered soil strata at the surface of the subgrade and the natural or non-weathered soil strata. To add a layer, the user simply increases the number of layers in the Number of Layers box. The previous slide had 4, and the new structure for Segment 1 now has 5 layers with 2 subgrade soil layers. For this case, the user needs to manually enter the layer thickness of the weathered soil layer. To remove a layer, the user simply reduces the number of layers. As a reminder, the layer thicknesses and other information or properties are imported from the other FWD data inputs from Step 1. Also, reduce the minimum elastic layer modulus to a very low value and increase the maximum layer modulus to a very high value so that the limits of the layer modulus are not reached during the back calculation process. And if the layer thickness file is not imported, all information on this screen needs to be manually entered for each segment. Finally, remember about the definition of a thin layer. The Layer 3 granular base in the screenshot has an average layer thickness of 4.84 inches, which is beneath a combined average layer thickness of 22.66 inches of a fractured PCC layer and dense graded asphalt layer. This certainly meets the definition of a thin layer. Thus, the fixed layer box should be checked so it is not back calculated. Trying to back calculate this thin granular layer would result in highly variable moduli that could go from very low to very high because the impact of this thin layer on the measured deflection basin is very low. Now let's move to Segment 2. As we stated in an earlier slide, the user simply repeats this process for Segment 2 and the other segments defined in Step 3, Final Segmentation. So as a reminder, let's overview some of the information we have already discussed. Layer thickness and other information are populated from other FWD data inputs from the layer thickness file. Remember, reduce the default minimum and increase the default maximum layer modulus so there is a low probability of reaching the minimum and maximum values during the back calculation process. And if thickness file does not exist, all information is manually entered for each segment. In addition, remember to check the Fix button for thin layers. As for Segment 1, a 5.89-inch aggregate base would be defined as a thin layer beneath the asphalt surface and fractured PCC layers. If left unchecked, the BcT will try to back calculate the elastic layer modulus for the thin layer, and it will be difficult to get reasonable results because the measured deflection basin would be almost independent of the thin aggregate base. Click on the Apply button to accept the values included for Segment 2 and proceed to Segment 3. Now, Segment 3. The 3 bullets shown on the slide are the same as on the previous slide. The example for Segment 3 will focus on using the Fixed Layer Elastic Modulus button. If a stiff layer is defined as a hardpan or bedrock layer or some other very stiff strata, the user checks the Stiff Layer button. If not included in the layer structure definition, a layer for a stiff layer will be added or replace the lower layer without a stiff layer. So, if the user clicks the Stiff Layer button, the user should check the other layers and make sure the structure definition and layer properties are correct. When a stiff or bedrock layer is included in the structure, the thickness of that layer will show a 0 because it is the last layer. The last layer in the pavement structure is assumed to be infinity and 0 designates infinity. A thickness of 0 cannot be entered for any of the other layers. Just a reminder to check the Fix button for thin layers. As for segments 1 and 2, a 7.02-inch aggregate base would be defined as a thin layer beneath the asphalt surface and fractured PCC layers. Click on the Apply button to accept the values included for segment 3 and proceed to Step 5 in the guided process because the layer structure simulations for all segments have been accepted. This ends Module 2, Session 2. The next module of the training course is Module 4, Session 3 on the BcT output and interpretation of results for rehabilitation design.